thank you. It's a pleasure to be a part of this workshop this year. Um, yeah, I should mention that I'm going to be talking about this interior point framework applied to problems coming from discretized PDEs, in particular for PDE constraint optimization. But the interior point framework that I'll be discussing here is also the same that is applied in the talk that follows mine from Socrates on contact mechanics and this algebraic multi-grid with filtering solver. Okay. Yeah, so I guess maybe to start like a motivating example for the incorporation of bound constraints in a PDE constraint optimization, in particular one that I looked at significant amount of time during my PhD work, which is the inversion for a non-negative ice sheet basal friction field. So on the right is the Greenland ice sheet, or like a cut of it, and there's an important PDE constraint optimization problem where one tries to infer a basal friction field that lives at the base of the ice sheet, quantifying how free the ice is to slide based on observations about how fast the ice is moving at the top of the ice sheet. This has implications for our ability to model, say, like future sea level rise, this sort of thing. Okay, but of course, incorporating bound constraints leads to challenges in the optimality conditions and such. And the goal of this work really is to kind of unite two different, two different approaches. One is there's a lot that has been learned in PDE constrained optimization, namely about the spectral structure of certain Hessians in this field and how to efficiently approximate linear systems, do preconditioning and this sort of thing. But here we'll be doing a more systematic approach for handling bound constraints, namely through the interior point method. Okay. So I guess a general problem statement of like what I'm looking to what my framework aims to solve is a problem of this form. We're trying to minimize an objective defined with respect to say U. One can think about U as the solution of a PDE which is parameterized by rho, and rho is going to be a spatially or temporally distributed parameter. And the objective is going to be made up of two pieces. One is a misfit term, quantifying some sort of discrepancy between the PDE solution and some available data about that solution, and a regularizer to make the inverse problem well posed. And some of the other terms here, there's a PDE residual R, and I guess, yeah, we have this bound constraint here on the parameter pointwise. Okay. Um, yeah, and so a common approach that I've seen in the PDE constraint optimization community for solving such problems is to do two things. One is to eliminate the PDE constraint. So that is, it's the idea that we can just optimize over, say, the parameter, and we know, and due to the uniqueness properties of the PDE, we know what the PDE solution U is for any given rho. That does lead to certain complication. Well, one, there's some benefits to this. One is that by eliminating, say, the PDE equality constraint in the optimization problem, that's you've eliminated one of the constraints, but also what's typically done a little bit, I'd say hacky, is to reparameterize this I guess this parameter here, rho, that is instead look at the optimized with respect to beta, so that for any real value of beta, like kind of by construction, rho will be greater than or equal to this rho L, because the exponential is strictly positive. Um, and so I guess in this approach, one has eliminated the inequality constraint and the PDE constraint. And that has its benefits. One has one is now optimizing with, say, a smaller number of optimization variables, and also, since one has eliminated the constraint, simple optimization methods are applicable, just like Newton or Gauss-Newton. But as a con, each objective evaluation requires a PDE solve. To evaluate this objective for a given rho, I need to solve the PDE and determine U of rho. And also this reparameterization can introduce higher order nonlinearities that one may be wanting to avoid. I guess to get a better idea of the problems I'll be looking at, here's an example problem I'll be discussing later, but just so you have a better idea. The objective, again, defined by discrepancy between the PDE solution and the data on some subset of the domain, and a regularizer, which penalizes two large values of rho and two large values of its gradient here. Okay, and I'll skip the second problem um, to be discussed later. Okay, so yeah, to get I guess a better sense of the algorithmic approach, yeah, what we do is the following. So cast the PDE into weak form and form a Lagrangian for the log barrier sub penalty problem. So this is kind of standard in interior point methods. One writes a log barrier objective where one has effectively penalized the parameter, kind of pushing it away from the lower bound rho L. And then there's a sequence of solves for the log barriers subproblem, decreasing that penalty parameter. Okay. One forms the interior point nonlinear optimality system, as shown here. So the stationarity of the Lagrangian, where these are first variations of the Lagrangian with respect to U and rho. And then there's a feasibility that the PDE constraint is satisfied here. Okay. Yeah, and so here we'll be using this a Gauss-Newton method to solve this linear system with stopping criterion defined by mass-weighted norms, in order that the optimization problem is sort of well defined in a like infinite dimensional sense, and so that the optimizer is not subject to like mesh dependent algorithmic behavior that one would typically have if one applied just a standard interior point method to it. Um, yeah, okay. So we'll be using something like a IP opt, but one that we actually implemented in MFEM with mass weights, a filter line search, and also the ability to really use a lot of the performant linear solvers, take advantage of all of that technology. Okay. And so, yeah, and so what follows is going to be really a discussion about how we solve the linear systems that arise when we do when we apply the Gauss-Newton method. So this is the interior point Gauss-Newton linear system after having done an approximate linearization and discretized the problem. So this is an important step that really eats up a lot of the computational time in solving these problems. And I should say that H is going to refer to the Hessian of the objective with respect to the state. R is the Hessian of the objective with respect to the parameter, and J are Jacobians of the PDE constraint with respect to U and rho. Okay, and some of that is here. Yeah, so JU is the discretized linear forward PDE operator. R is this regularization term, and having used a combination of like squared L2 and squared L2 penalties on the gradient, this is the form of the regularization operator, linear combination of mass and stiffness matrices. Um, and while the interior point method is a robust method for nonlinear, non-convex optimization and has been really performant for large-scale constrained optimization problems, I think maybe one of the biggest challenges is there is some sort of inescapable source of ill conditioning that enters these problems, and this is due to this Hessian of the log barrier term. For this problem, it is this a lumped mass matrix and some diagonal matrix that becomes very ill-conditioned as we approach the optimizer, as we reduce this barrier penalty term. And so in order to design a scalable framework to solve these problems, we're aiming to design an iterative linear solver to solve this linear system. But yeah, this can be challenging for it for that purpose. Okay. So we actually tried a number of things, but one thing that I'll show works actually pretty well, and it's kind of fairly simple, is using what I'll refer to as a block Gauss-Seidel preconditioner under a suitable permutation of its rows and columns. It is a block upper triangular. And this preconditioner is formed just by eliminating this 3-2 block here, just zeroing it out. Then there's another approach that we have for where we actually can use CG for that I'll discuss time permitting. Okay, so this block Gauss-Seidel preconditioned matrix is similar to the following. So it's block upper triangular and has identity, the 1-1 block, that's good. And then it has identity plus some perturbation on the 2-2 block. Now, this perturbation, some of the terms mentioned before, the regularization operator, the Hessian of the log barrier, but then there's this new term, H hat D. This is a term that is well known for and comes about in reduced space approaches for PDE constrained optimization. This is this reduced space data misfit Gauss-Newton Hessian. And what has been studied actually fairly extensively, it's been proven for some simple problems and demonstrated numerically for others, is that this reduced space data misfit Hessian preconditioned by the regularization operator actually has eigenvalues that decay rapidly to zero and in a mesh independent fashion. Um, some fairly simple analysis that we did, we were able to show that the eigenvalues of our preconditioned, this block Gauss-Seidel preconditioned interior point Gauss-Newton matrix, is the eigenvalues are bounded below by 1 and bounded above by 1 plus these eigenvalues, which again decay rapidly to zero in a mesh independent fashion. Furthermore, this upper bound does not have any components that are specific to the interior point method. And specifically, there are these interior point method specific components that lead to ill conditioning, such as the Hessian of the log barrier. Yeah, and so we can conclude from all this that this preconditioner one should behave in a mesh independent fashion, and also it's not going to be impacted by ill conditioning due to the interior point method. Okay, but I guess the maybe to explain a little bit about the cost to apply this preconditioner. Yeah, on a suitable basis, it's block upper triangular, and so there's three block solves that need to be performed in order to apply the A tilde inverse. There's a JU inverse transpose, so linearized forward PDE, adjoint PDE solves, and here we'll be doing an AMG CG solve for this here, and here actually this Hessian of the log barrier term, because it is positive definite and diagonal, it serves to improve the diagonal dominance of the overall operator and makes it even more suitable for AMG CG solves. Okay, and so I guess a little briefly, we could also we have an approach, preconditioned CG approach. So one can form the Shor complement by eliminating U hat and lambda hat, as show, and the resulting linear system is shown here. And then we could use a regularization and log barrier Hessian as the preconditioner, and then the eigenvalues, and then the resulting linear system, this preconditioned system here is actually identical to that of this 2-2 block that we looked at earlier. And we know the eigenvalues of that object as well. Okay. Okay, so this is probably, yeah, I guess preaching to the choir here, but yeah, really happy having used MFEM for this approach, for this work. Um, yeah, so mainly using uh, yeah, the finite element discretizations and the algebraic multigrid preconditioners. Yeah. Okay, so now for some numerics. So for the first example problem, this is a nonlinear elliptic PDE and bound constrained optimization problem that I showed a little earlier. Um, so we have the following nonlinear PDE looking to invert for this diffusion coefficient. This is a time independent problem, as you can see. The domain is a unit square, and we'll be taking observations of the PDE solution on the left-hand side of the domain. Okay, I think that's all I want to say there. Okay, um, so there is a matter of effectively choosing these coefficients in the regularization term, the gamma 1 and gamma 2. And this is a fairly standard approach, but I just want to mention that we chose the regularization parameters through the Morozov discrepancy principle. That is, we look after having solved this optimization problem for a given regularization values, we look at the discrepancy between the solution of the optimization problem and the data. And we compare that to this synthetic noise that we use to corrupt the data itself. So we have some data field UD that we added some noise to. And then we, yeah, choose the regularization parameter so that the noise matches the discrepancy. And that's just really so we don't over or under fit the problem. And on the left is the spatial structure of the noise. So this is a sample of the noise, which is, yeah, also well defined under mesh refinement, using a elliptic PDE operator as the covariance there. Okay, so this is for the regularization parameter that balances the discrepancy of the noise. Yeah, this is the solution of the optimization problem. So this is this 2D problem. Just want to show that they look fairly good. This is the solution of the optimization problem in some true field here, and then the true PDE solution, and then some the data on the very right. Okay, but maybe a little more interesting is how this algorithm performs under mesh refinement. Um, so here we have like a sequence of solves of the with different levels of mesh resolution from coarse to fine meshes reflected in the dimension of the discretized parameter field from hundreds of thousands to hundreds of million. And the average number of interior point steps to solve this optimization problem is fairly fixed at 28, 29. So we're seeing some mesh independent performance of the optimizer, which we're happy with there. And then we look at the average number of block Gauss-Seidel preconditioned GMRes iterations needed to solve that interior point Newton matrix, Gauss-Newton matrix in our system. And that is also pretty fixed as we increase the mesh resolution at about 6.5. And the CG iterations are also, yeah, showing mesh independent behavior. Okay. Yeah, and so I guess for this approach, we now have like an algorithmically scalable method, and we're able to use, for this problem, we're able to use AMGCG to solve the regularization systems, and as well for the linearized forward and adjoint solves needed in the application of the preconditioner. And with that scalable method, we're able to then get a overall scalable means to solve these optimization problems. So this is the time needed to solve the optimization problem for different levels of mesh refinement, and where we're varying the number of CPU cores, and we get some good, yeah, some good strong scaling there. Okay. Yeah, and so the what I've shown here is some numerical evidence for one of the claims that I made earlier, that these preconditioners are robust with respect to the ill conditioning coming from the interior point method. So this is just one optimization solve, and from left to right, we're looking, the optimizer is progressing. And while that optimizer is progressing, this log barrier parameter is decreasing in purple, like 10 to 10 to the minus 7. And the interior point Gauss-Newton matrix is getting more and more ill-conditioned as we progress from left to right. But the preconditioned matrices are fairly insensitive to that, reflected in the number of preconditioned Krylov-subspace iterations needed to solve these linear systems, sort of flattening out here at about 10, 11. Yeah. Okay. So for one final numerical example, looking at a time-dependent problem where the parameter is now the initial condition of this time-dependent problem. And where we are observing the PDE solution at the final time Yeah, that is where we're taking our observations at the final time and also on the left-hand side of the domain, as in the previous example problem. Um, and this was really more, the following is a little bit, is in response to one of the reviewers that was wanting to see how this method performed if we over or under regularize the problem. And so maybe this will help also give you a sense of what that means. So these are solutions of the optimization problem for different regularization values. So on the, I say maybe in the this second to the left plot, this produces a solution that matches pretty well the true solution here, but on the left we have too weak of a regularization, and so the solution of the optimization problem then becomes more sensitive to the noise and it's a little funky. And if we over regularize the problem, then the objective of the optimization problem is one is to reduce the L2 norm of rho. And so it actually becomes too small. This is 2 orders of magnitude too small. Okay. So we then looked at the scaling of the method, algorithmic scaling of the method for like under regularized and over regularized problems. Again, we have sequence of increasingly refined meshes, and in parentheses are the number of interior point iterations, and to the left are the number of GMRes iterations. And in any one of these columns, we have mesh independent performance. Then as we go across columns, the number of interior point iterations is going to change because we have a different optimizer, so that the path, the optimization path is going to change. And um, the number of Krylov-subspace iterations actually also changes because it depends on the on properties of the PDE constrained optimization problem. Okay. So to conclude, yeah, presented a method for PDE constrained optimization problems that respects the nature of the infinite dimensional problem and hence is um, displays mesh independent performance. The ill conditioning was handled by preconditioners that exploit PDE constrained optimization structure. Interested in applying this framework to a broader set of problems, and any discussion and feedback in this method, this solver is available here. And yeah, with that, yeah, thank you.
Hi, I have a question. On slide 25, when you look at the under regularization, it looks like it's losing the mesh independence. Do you understand why that's the case? Is the regularization needed to get the mesh independence?
What I believe is occurring there. So there's this phenomenon of like regularization by discretization. So maybe because you have too coarse of a mesh, the mesh doesn't support you having like too oscillatory of a solution, right? And so what I believe is that like yeah, earlier on there's yeah, going to be some regularization by discretization occurring, but then that will eventually go away if I were to look further out in this table. And I was kind of seeing like kind of smaller jumps as we go like further down the table. So yeah, my hypothesis is it's regularization by discretization there.